Guys, welcome back. Well, I've been struggling lately in getting my SCT back outside and trying to do some useful imaging before galaxy season ends and not having a great deal of luck. Lately, I've been finding my guiding is just a lot worse than it was last year when I was using the SCT, so I've been going into some of the PHD2 logs trying to understand what the fundamental problem is. I think it's associated with the RA gear train. Anyway, I thought I'd share with you a little bit of the guide log analysis that I've been doing. Just maybe it'll give you some clues for improving your guiding. Now, one of the things that we got to do before we do any guiding is do a pretty decent calibration, PHD2 calibration. Anytime you change the orientation of your guide camera, change the orientation of your off-axis guider, etc., you need to redo the calibration because that's going to change things. And one of the challenges, extra challenges you have when you have an off-axis guider is to find a bright star to do the calibration with. You want a good signal-to-noise ratio. You also want it to be up near the meridian and near the celestial equator. But one of the viewers commenting on a previous video clued me into a feature in Stellarium that's particularly useful for this effort, and I thought I'd share that with you. The whole idea is to move a bright star into the field of view of the off-axis guider, hand that to Nina, slew the scope over to a location that you mark in Stellarium so that the guide star is in the center of view of the guide camera, and then do the calibration. And that's what I want to demonstrate here. Let's just go over to Stellarium. One of the advantages of picking a bright star for PHD2 calibration is that we might get away with doing the calibration when it's dark, but not yet dark enough to do any real imaging. So I've got a situation here set up in Stellarium where the sun has just set. It's below the horizon, which runs in right along here. And this blue line represents my horizon with trees, fences, adjacent houses, etc. Now, what we want to do is to pick a star that's near the meridian, but on the west side, and near the celestial equator, so that we can decouple motions of declination on the imaging camera frame from RA motions. That's one of the advantages of doing a calibration near the celestial equator. A second point is near the meridian. We want to be away from any atmospheric disturbances near the ground. So if I look here at this time, I'm looking for stars near the equator, which is the blue line down here below this green line. So this is the west side of the meridian. There's a potential star, and Hetze is a perhaps even better star in that it's got a declination angle of only about half a degree. So that's a pretty good location to go for. So what we would do is pick Hetze, then go into our ocular section and pull up the image with our guide camera and off-axis guider oriented. Another good thing about this technique is it gives us an opportunity to verify that we have the off-axis guider orientation set properly. But at this point, Hetze is in the center of the field of view of our imaging camera, which is not what we want. We want Hetze to be in the field of view of our camera. And so I'm going to move that up here into the center of the field of view. And here comes the trick. I'm going to move down to the imaging camera at the center of the view of the imaging camera and press shift and left click, and that creates a marker that is now fixed in the star field. So it will move. As you see Hetze here move, we're not connected to anything, so you can see it slipping out of the field of view. The marker that we just put down is also slipping out of the field of view, so it's fixed in the star field. And now all I have to do is click it, and then I can go over to Nina, go over to the framing assistant, and load those coordinates in. So here we are focused in this region where there's nothing really to look at because we're interested in the guide camera. And then I could just press this button and slew over to the target. Now I can't do that now because I'm not connected to a telescope. However, the other night when I was out applying this technique, I did record the screen. So let me show you what that video looks like. All right, so I've moved Hetze into the center of the field of view for the guide camera, and I'm positioning it. Now I'm going to press shift and left button, and there we have the marker. Now I can select the marker and go over to Nina, which is now connected to the telescope, and go over to framing assistant and bring the coordinates in from Stellarium for that marker. And you notice that in the field name here it says marker 3, so it's not like it's some NGC number or or some star designation. It's the marker we put into the Stellarium field of view. And now we've loaded it in, and so I'll just slew over to the target, and you can see in the Next Remote handset, or the replica of the handset using the Next Remote software, that spinning line on the right side of the display indicates that the scope is actually moving. We'll do a plate solve and make sure that the mount is truly centered as best as possible, as best it can, at the center of that image indicated in the Stellarium view. There's the picture. And I'm using Plate Solve 2 here because lately, for some reason, I'm having issues with ASTAP solving images of these small number of star-filled images I get using my SCT, even though I used it quite successfully last year. So now we go back into PHD2 and turn on the guide camera, and there you can see it. There's Hetza, very bright star. If you click on it, it's saturated 9 ways from Sunday. So if I dial back the exposure to maybe, I don't know, 0.2, and nope, it's still quite overexposed. So we'll go down to 0.1 seconds. And that's reasonable enough. So we have a very bright star, so that's Hetza. We have confirmed that our off-axis guider is actually set up properly, and we can use a short exposure setting, and we'll go ahead and force the recalibration to have it calibrate PHD2 for this particular orientation of the guide camera. And the calibration process is going to move it independently, first in the RA direction and then in deck direction. And so it's finished collecting the data it needed for calibration, so it's going to move the guide star back to its sticky lock position. And now it's always a good policy to go back to the Tools menu or look at the calibration data. There it is, and that's pretty decent. If you didn't like that, you could redo the calibration, but that's good enough for now. And so that's it. I think it's a pretty neat trick to use the marker function of Stellarium and then pass that to Nina in order to place the imaging camera where you want it so that you have a bright guide star where you want it. Well, after I did the calibration, I moved over to the target, which was M94, and did a period of guiding there and also ran the guiding assistant. I'm going to go over to the PHD2 log viewer to pull up that data so I can show you the data that we'll be looking at in this video. Now, if you don't have the PHD log viewer and you want it, you can go over to their website and scroll down to the bottom, and you can see the PHD2 log viewer. Just click the link and then download this program. So here's the PHD2 log viewer, and I'll open up the log file. Now, up in here, you can see that we have several entries. Each time you press the Start Guiding button, it will record a little entry line in this table. Now, the first thing we did here is do a calibration on a particular star, and then I moved over to another star and did another calibration, and then shortly after that, I started making a run with PHD2 in the guiding mode, and this is what I recorded. So I started guiding here, and PHD2 is doing its thing, doing guiding, and then about halfway into this, I went over to the Tools section and selected, with the guide star in place and in the middle of guiding, and pressed the guiding assistant. It's tracking the guide star, but it's not sending commands to the mount to correct for the position of the star. And so as a result, the star starts to drift off in deck and drift in RA because the polar alignment is not correct. Now, what this guiding assistant will do is give you an estimate of your polar alignment accuracy amongst some other things. Here, I'm primarily interested in how effective is the guiding done when PHD2 is issuing commands versus what commands should it be issuing, or what kind of errors does it have to compensate for given this is what it's seeing without issuing commands. And so we're going to take a look at the data that we have before we turned off the guiding, and we'll see what the analysis looks like of the data we have after we turned off the guiding. This is the data we recorded when the mount was guiding. The error that I'm getting is about 0.8 arc seconds RMS in the RA axis, which is larger than what I've been seeing. And I'm getting about 0.49 arc second RMS in the declination axis, which is also a little bit larger. But again, the deck axis is going to get some leakage of what's going on in the RA axis, and so it's going to be affected a little bit by the RA error that's going on. And then the total error is 0.945 arc second RMS. But for the most part, that's much higher than what I want. I prefer to have guiding below about 0.8 arc seconds And if I'm really lucky, I'm down around 0.6. In the unguided portion of the data set that we were looking at, so now I've engaged the guiding assistant. It tracks the position of the star, but it doesn't make any corrections. The guiding assistant tells me that the polar alignment error was 3 arc minutes, which is responsible for this more or less linear drift in the declination axis. And there is also a linear drift in the RA axis. However, there's also some significant periodic motion going on in addition to the drift. The key point here is that if you were perfectly polar aligned, then you wouldn't have these linear drifts, and these curves would lie right along that green line, more or less. And that's what we can do over here. We can just subtract out the linear trend. And so this is essentially what I would have with my mount, perfectly polar aligned, but not guided. So it's just doing the best it can, subject to the imperfections in the RA gear train. And you can see there are some rather significant periodic error here in the RA axis, roughly a total from peak to peak of about 25 arc seconds. I think that's kind of typical for a CGEM back in the day. And then we also get the deck motion, which, like I said, it's getting a little bit of disturbance from the RA axis feeding into it. But by and large, what you're seeing here is motion primarily driven by seeing conditions. So I would expect the RMS error here, which is measured at 0.6 arc seconds RMS, to be something around 0.4 to 0.5 arc seconds RMS for seeing in both axes, frankly. And everything else above that is the mechanical sources of error that are adding in this. A total error here of 6.7 arc seconds RMS is way too high. I need to be around 0.8 arc seconds RMS to get decent images. So clearly I need to turn PHD2 on in order to tame these significant excursions that are primarily coming from the RA gear train. The best way to analyze time series data when you have periodic contributions to the data, such as a rotating gear, is to do a frequency analysis. And Joseph Fourier came up with the Fourier transform that some of you will have heard of and possibly even used. But the idea is to take a time series and convert it into a set of frequencies with corresponding amplitudes and phases that are added together to make up that original time series. The thing that jumps out pretty quickly is that there is a significant peak here, a significant periodic contribution, which is in fact the worm gear period of 478 seconds. I've got frequency plotted along the horizontal axis here in terms of millihertz. So to get from 478 seconds and to millihertz, you would do the inverse of this. So 1 divided by 478, that gets you into hertz. Multiply it by 1,000, and that gets you into millihertz. And if you do that, the worm gear frequency is 2.1 millihertz, which puts you at about 2 here on the graph, and that's why there's a big peak there. The amplitude for pointing error in this plot is not the peak-to-peak amplitude, it's the zero-to-peak amplitude, and so that means we're getting a peak-to-peak contribution of about 14, almost 14 arc seconds out of the 25 arc seconds that we were seeing is due to the worm gear fundamental period. The first harmonic, and that's at 239 seconds. And then we have a unique feature of the CGEM that it has what are called subharmonics. And you can get a subharmonic in a gear train when you have, in this case, the worm gear that has a certain diameter meshing with a gear, in this case, of about 3 times that diameter. So in other words, the worm gear has to go around 3 times before you see the full period of that larger gear. In addition to these major harmonics, these are the primary sources of pointing error, there are also some additional peaks in here associated with higher harmonics and perhaps ball bearings that are also contributing to the pointing error. So all of these frequency components plus the seeing add together to make the total error that we're seeing in the RA axis. The mechanical fingerprints of the CGEM are all over the frequency domain analysis here. PHD2 has implemented some time back the Predictive Periodic Error Correction algorithm for the RA axis. Now here the idea is to develop a periodic error model. Now in this case, what you're seeing here with that orange curve is a 4-term model that I produced to get the best fit of that model to the available data. And as you can see, the orange curve does a pretty good job of capturing most of what that blue curve, the original raw data, is doing. And then once you have the periodic portion of the error modeled, you can use that in a predictive fashion by simply issuing the commands before the error occurs, and that way you never actually see the error. You only have to deal with what's left over. So I think this predictive PEC algorithm in PHD2 is pretty effective for mounts such as mine that have fairly significant mechanical induced or gear train induced errors. This is the PHD2 menu, and in the advanced settings in the algorithms tab, you can see for right ascension I have the predictive PEC algorithm selected. There are some parameters here that I should start to play with a little more, and then within the expert field here there are a number of parameters that frankly I've never touched. And so I'm going to read up on this algorithm and learn a little bit more about what these parameters do, and maybe I can dial in the correct parameters for this predictive periodic error correction algorithms, and hopefully pull out that little bit of extra error on the mechanical side that'll give me the guiding I'm looking for. Now, there is a new multi-star guiding algorithm, but the thing to keep in mind here is that the multi-star guiding is done in addition to these other algorithms, so you can use predictive PEC algorithm with the multi-star option selected. Multi-star is not going to improve guiding when it's mechanical errors that are responsible for the guiding errors. It's only going to reduce errors associated with seeing. Let's compare the guided response to the unguided response. The blue curve here is the data recorded using the guiding assistant, but no guiding commands are being sent to the mount. And so this is the error I would have in the RA axis if I were issuing no commands but the mount were perfectly polar aligned. On the other hand, in the guided configuration, when PHD2 is actually sending commands, you can see that I get the orange curve. What's amazing here is how effective PHD2 is at reducing these significant mechanical induced noise. So this worm period is dropped by more than a factor of 10 all the way down here. The first harmonic is reduced significantly. Even the subharmonic is reduced to almost nothing. There's still something left. You still have little peaks down here indicating that some of those errors are sneaking through, and I think that is the primary reason why I'm having a bit worse guiding than what I used to get. We shouldn't lose sight of the big story here, which is that PHD2 does a remarkably good job of reducing these long period or low frequency errors such as polar alignment and some of the primary harmonics in the gear train. I've been seeing fairly poor guiding performance lately with my SCT and CGEM. It's never been awesome. It's been acceptable in the past, and right now the error is just beyond the acceptable limit. One of the things that I found to be useful is a feature of Stellarium that I did not know existed, and one of the viewers pointed it out to me. But it's this idea that you can set a marker that moves with the stars, and so that allows you to position your imaging camera so that your guide camera is looking at a bright star. There are two benefits here. If you see the guide star in the field of view of the guide camera, that confirms that your off-axis guider is oriented properly. It's where you think it is. And the second thing is when you're doing a PHD2 calibration run, you're using a star with a very high signal-to-noise ratio, which means you should get some much higher quality data for the calibration, and also given that it's a bright star, you might be able to get away with doing a calibration while it's dark, but yet not quite dark enough yet to do any imaging. PHD2 has a guiding assistant feature. If you start off guiding and then switch on the guiding assistant, it will stop sending commands to the mount to chase the guide star, but instead it will track the guide star and record the data. And if you go back and look at that data, perhaps just with something as simple as the PhD log viewer program that I showed you and that they provide from their website, you can get some good insight as to whether your mount has significant errors associated with the gear train or whether it's primarily seeing induced error that you're dealing with. I recommend that you try out the predictive periodic error correction algorithm if you have a mount with high gear train noise like I do. The predictive PEC algorithm does a really good job, better than some of the other algorithms, for dealing with gear noise associated pointing error. The multi-star guiding algorithm is also useful, but only for reducing random seeing-induced error. That lets you use a lower exposure setting, in other words, guiding command update rate, so that you can do a better job of dealing with gear train noise. Now, if you're using PHD2 or maybe even some other guiding software, don't worry about training your mount for periodic error correction. It's no harm if you do. If you want to do that, go ahead. It probably won't help that much because guiding does a heck of a good job of dealing with long period errors. I've still got these large excursions that I'm still trying to deal with, or at least excursions that are large enough to cause guiding errors. I think they're associated with some higher frequency mechanical noise, and maybe the answer is to dive into some of the more advanced parameters in the predictive PEC algorithm and see if I can't just squeeze out a little bit better performance. No good news here, guys. That's about all I've got. Clear skies, and hope you have better guiding than I've had. See ya.